же выпил шампанского. Представляешь?
Да,
Так.
это что-то да значит.
Да.
Окей. 1 minute left, so I announce a continuation of the previous talk by Vladimir Rubtsov, and he will speak, and I hope we will discuss some approaches to theory of homotopy structures on PDEs. Volodya, please begin. You are welcome.
Thank you very much for your invitation and for your you are courageous persons came to the second talk after the first one. I didn't finish the first, and I hope to finish second. And special thanks to Raffaele, not only because he has the courage to come to hear what he knows better than me, and than I, and also for his help with when I wanted to write this paper. As I told you, it is based on our paper with my colleagues from France, Jean-Pierre Magnou, and from Chile, Enrique Reyes. And we had a very modest aim, just to try to find some non-trivial examples of the structures of homotopy type related to horizontal and vertical complexes in Vinogradov setting. So I just remember the key moments of my first talk. I will be very, very quick, not to spend time, and just after introduction and the basic definitions of the homological and algebraic structures which I need in the realm of associative graded differential algebras. I reminded main definitions of minimality and formality, and I remind the Dennis Sullivan when he was the origin of this. One of the origins. Another origin was due to our old friend Jim Stashev, and he considered so-called the question of rational homotopy type description and formality of Kähler compact manifolds. And it was discovered in mid-70s that not all varieties are formal, and the main simple example, it's so-called Iwasawa type varieties related to Heisenberg group, which is a quotient of this 3 times 3 matrix group over integer lattice. And the cohomology of this homogeneous space has a bad property. They are not formal. And that I explained more or less in details. And then I also explained how it relates to, to the description of formality of simply connected Kähler manifolds, compact Kähler manifolds. This based on some simple properties of Hodge structures related to these varieties. And then the second ingredient which I explained was so-called homotopy associative structures. And this is a main input of topologist. One of them is Jim. I mentioned in his thesis about Hopf structures, homologies of loop algebras. And second important person in this was May, who wrote a small book about these higher structures of associative type. So this definition is based on so-called Jim Stashev identity for higher multiplication. I explained what it means, and then it is just a generalization of associative algebra structure using higher multiplications. It's of course it's a kind of jargon. Higher multiplications. It is operations indexed by an integer index n. For n equal to 2, it is a real multiplication or quasi multiplication. It is multiplication um, satisfied to usual associativity condition up to some higher condition. Then compatibility of this higher condition gives another condition for M3 and M4, etc. And then these equations of these equations are introduced by Jim, I suppose the first. And then the question, if we have two algebras, and first of all, what what condition of minimality impose on my operation M, and if you have this a infinity structures, then minimality by definition it is first M equal to 0, and then we have also condition on transportation or transfer associative structures from one associative algebra to another complex. So we have two complex, one complex of associative algebras, and then we want to construct with the hope of this initial associative structure A another structure on its homotopy dual, like people say. And this condition was described in the following graphic way. So let's suppose that we have an associative multiplication, then we have this condition, as I told you, and then we compare this with operation on the second complex, and this associativity produce the element which is called associator, and this associator in terms of new data which is given by this operation P and I from our definition here gives you the associativity up to the nullity of this element, which is called associator. And then all of these Jim Stashev conditions, compatibility conditions, can be written in graphical way as operations in some complex. And for example, a condition that associator is equal to 0 means that this tree with three branches is closed in complex of third tensor degree. This I explained also. And then I formulated not very difficult but very important Kodeishvili theorem, which imposed some conditions when this associative homotopy property can be used to transfer associative structures. And then he proved that our operators which satisfy these Stashev equations, mu sub n, define on H associative product by the formulas which we considered. And this means that a real associative structure can be obtained from homotopy associative structures or satisfying the, and that we will have as example in the second part of my talk. In fact, a little bit later, Sergei Merkulov made more precise this generic statement of Kodeishvili, and he considered the transfer theorem, which was influenced by another type of formality property. He wanted to extend formality property from Kähler manifolds to so-called Calabi-Yau manifolds. This I tried to explain also last time. And then he introduced the following algebraic data, which we will use very, very often in our approach to PDEs. Namely, we have superalgebra, differential graded superalgebra with differential D. And then we suppose that this complex has a very, very special subcomplex, which we denote by W, and some operator of degree -1 Q, which also will be important for us, such that the image of the map identity minus bracket D and Q always lies in this subcomplex. And then using this subcomplex, we define also analog of Jim Stashev construction. Namely, we defined lambda sub n operators from tensor product of algebra and of degree 2 minus n, and lambda 1 for n equal to 1 is defined by the condition that the Q and lambda 1 are almost inverse up to sign. And
I'm sorry, I assume that in the last formula, this S plus P and so on are in subscript, yes?
yeah, it is, yes. So I'm sorry. It is.
Okay.
I told last time that it
It's
is
clear.
my.
Yeah.
I didn't change. Sorry. I forgot about it. I didn't change it. Anyway, we have this recursive definition, and this recursive definition we will call Merkulov assumption. Then Merkulov theorem with this Merkulov assumption gives the following: if we have our differential graded algebra with this assumption, then we can define another family of maps from tensor degrees of this on this subcomplex, such that the first member of this line of degrees, it's our differential in my algebra, and n's defined recursively through this operators lambda from assumption. So this map, family of maps parameterizing by n, satisfy Stashev identity, and then because of it, we can say that our subcomplex carries a structure of A infinity algebra, homotopy associative algebra. So it's a very nice result of Merkulov. Of course, it looks very, very formal and abstract, but after details, which I explained last time in very very precise way, spent a lot of time. After this precise definition, we can apply this to the following case. If we consider family of our maps lambda, which we defined in introduction to Merkulov theorem, then we can define multiplication operators m sub n on homologies of algebra, and supposedly we have this we have some minimality. So the first operator M1 is equal to 0, like I reminded. And then we have a structure of homotopy associative algebra on my um, homology. And F is a family of maps minus q times lambda n, gives you a quasi isomorphism of A infinity algebras structures on homologies and initial differential graded algebra. And this we will call Merkulov model or minimal model by an analogy with Sullivan minimality for DGA. And this Merkulov specification gives a very nice application, as I also tried to explain last time. Namely, we can consider on compact Kähler manifolds with so if it is called compact Kähler, so we have co-differential delta with respect to the corresponding Kähler matrix, and then we can consider delta closed form alpha and beta. But if we have delta closed alpha and beta, the wedge product of this form is not delta closed. What we can do to cure it? In fact, we can define new multiplication. We can take old wedge product of our form and restrict it to the kernel of our co-differential. But if we check carefully this, then we have that this new definition is not completely good, because our circ operation is no more associative. But Merkulov cleverly demanded that this product circ associative up to higher conditions. It means that we have A infinity structure on our manifold. And in fact, we can define different A infinity structures on our manifold. We can make different choice of Merkulov data. So we can have different choice of subcomplex W, and we have a real Hodge-de-Rham A infinity structure which correspond to this choice of Merkulov data. We have Dalbo A infinity structure, Hodge-Dalbo A infinity structure, when we have as a subcomplex which is a kernel of D partial dual. And finally, the most interesting case, of course, it is the case when we have in the case when we have not simply Kähler manifold, but Calabi-Yau manifold. Then we have another third A infinity structure, and this A infinity structure, I don't want to go into details because it's a very long and deep story, but it is very important in mirror symmetry. It was in so-called Kontsevich-Barannikov differential graded algebra, which appeared in their studies of homological mirror symmetry. And then I wanted to stop here, and it was time to stop here. So my second half, in fact, started here with a reminder about what Luca Vitaliano did. And as I told you, it's shame to me, because when we started to discuss it with Enrique and Jean-Pierre, we just were absolutely stupid, naive novice in this business, and we didn't know who did something. I asked everybody. I asked Joseph. I asked Alec, and they said, "No, we don't know." I don't know. I don't know. Raffaele also said that he doesn't know about formality and other things related to Vinogradov approach to geometry of PDEs. And the only person I didn't ask it was Luca Vitaliano. And in fact, in 2012, 2013, Luca also thought about it. So, in fact, I could forget about what I told you before and started from this Vitalian interpretation of Merkulov transfer theorem. The only thing which motivates our paper with my colleagues is that Luca, a part of general statement, did no computations and examples. He didn't study formality, he didn't study minimality for various complexes arises in the approach of Vinogradov in this setting. And I don't know why they didn't, neither he nor his colleagues with whom he tried to discuss it. Maybe it was because they were charmed very much with higher structures, and only higher structures themselves were their aim. And also, probably it was because Luca more interested in not associative part of the story, but though he formulated a theorem for associative part also, but also he was interested in Lie algebraic part, L infinity structures.
Володь, давай, let's go closer to
Yes.
the main topic.
So I will I want to say that I will be very quick with
No,
definition.
you were very long with something that, for example, with scalar manifolds, which has no relation to our topic. And now you want to be quick. No, let's
Yes, now I
go
can be
now.
quick. I can be quick. So let's consider that we have a pair, a diffiety and a Cartan distribution C.
So what is diffiety from your point of view?
Well, the divided is just like you say, it is just subvariety in infinite jets, which comes from
Okay.
some, yes.
Infinitely prolonged
Yes,
equation.
yes, infinitely prolonged
Yes.
equation. Yes, it's a differential. So I will try to say more if I need, and because my all my examples will be in very explicit coordinate way. I will just remind what I have in mind in local coordinates more. But I start with what Luca formulated invariantly. So he considered the function on diffiety as algebra, and then he considered various modules over these algebras. First module, important, is a D-bar module of transversal differential operators. He defined the quotient of differential operators on diffiety over the so we have a ring of differential operators D of E, and also we have a action of this Lie algebra Cx on the ring, and then we have a quotient which we define
What is CX?
Cx. What how to say Cx? It is just, well, let me be more precisely, to be more precise here. Just a moment. I will try to write. So we have x. Sorry. I'm sorry. Just a moment. For a moment, I will open free part just to write. Так. Don't. How to do it? No, I completely forgot how to do it.
No, just say what is it?
Well, it is just you have this it is involutive distribution C, yes?
Yes.
So if we have involutive distribution, then Cx it's a corresponding Lie algebra.
So
Involutivity
this
of
is
what is, yes.
The model of
So you
vector.
have a vector fields and you have
Yes.
a closed closed subalgebra.
Okay.
Yes,
Total derivatives.
yes, total deriv. Yes,
Okay.
absolutely. So we have write it. D bar
Yes.
equals sum of yeah, okay.
And
So
you
total
act
derivative by all the all.
you act by total
Yes,
derivatives from the right.
yes, yes,
Okay.
yes. And then we have a
Yes.
transversal
Yes.
x
Very.
bar. X bar, it's transversal. Okay. Then also we have a part of Cx, we have a C lambda 1 module annihilators. It's an analog of forms. Okay, it is
Yes.
also C infinity
Yes.
of a module which
Yes.
annihilates Cx.
Cartan forms. Yes.
It's
Well.
Cartan forms. And
Yes.
involutivity means that these Cartan forms define the good ideal in
Yes.
the
Yes.
exterior algebra of the
Yes.
phi in the corresponding quotient graded algebra. It is a so-called longitudinal to Cartan form.
And what is this homology group? H bar, E, D bar.
So you have this d bar. It is
Yes.
this differential operator. Okay.
Yes.
So you have operator d ram, and you have d bar corresponding, and h bar is homology.
So I'm sorry. Where is the RAM?
So this you have a Ram algebra. You have
Who
lambda.
is the RAM algebra?
You what the you have a lambda of defined. Okay, you have a quotient
Yes.
over this ideal. So you have lambda bar. Okay, lambda bar of e, and you have homology
But
of.
why homology with coefficients in D bar?
No, no, it's not coefficients.
Ah, it's a homology of the pair.
Yes,
So okay. So
yes. Yes, yes, it's homology of the pair. Coefficients you can define, of course, if you have any differential modules, you can define the coefficients as well. But this I want just to see that how many different homology I
so
can.
H bar is horizontal complex.
It's a
Horizontal
horizontal complex will be, yes,
Okay. Why will be?
and then will be in details. I will
Yes.
explain it in the case of variational complex in coordinates. What also I want to remind it is that Luca rewrote the Merkulov transform data for this complex. So he considered a infinity structure. It is his result that there is a infinity structure in lambda bar tensor d bar with d bar differential, which defined by analogy of Merkulov data in of this homotopy dual pair. One complex, it's a complex d of lambda bar with operator bracket with d bar, and another it's lambda bar tensor d bar with differential d bar on this quotient of operators, and the corresponding data satisfy to this operator equality. Composition IP, it's a morphism from lambda.
And how P and I are defined?
Yes,
Yes, what?
hmm?
Yes, what?
One can define I and P in such a way that this homotopy data satisfied.
But how to define them?
This is a projection, and this is an inclusion.
I don't understand.
Well, I will explain it in details in
Okay.
coordinates. And so we have this DGA, and one structure gives you another structure up to homotopy. So it's Merkulov theorem gives on this A infinity structure, which comes from homotopy A infinity, from homotopy structure on this. This what result of Luca. And now
just Володь,
I will explain now.
no. I mean notation. What does the notation d of lambda bar blah 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 means? D what does this d mean?
It's differential operators on lambda. So you have lambda bar, and you
Yes.
have operator.
Lambda bar are Cartan forms, yes?
Yes, lambda bar
Yes.
Cartan form.
So
And
these
you have
are
operator D bracket with D bar. Bracket with D bar.
Bracket of
which acts on this lambda bar. This differential. This is the differential algebra which denote of this structure. So it is, if you want, it is cochains. You have, it is differential algebra which defined by lambda bar and with this operator.
D means now not vector fields but differential.
No, not vector fields. It's differential operator.
Okay.
It's differential algebra notation.
Sorry, Volodya, please, lambda bar are Cartan forms or horizontal forms?
Horizontal forms.
But
and
you
then
told,
how
Volodya,
total derivatives acts on D bar by left composition?
Alec, I'm sorry, but Volodya said before that lambda bar annihilates total derivatives.
Yeah.
So it's these are Cartan forms.
No. Cartan forms, they are exterior algebra of C lambda 1, yes?
No. Let's. You told when we started to discuss the equation case that lambda bar denotes the module of forms that annihilate this how dxd or dx annihilate total derivatives. So they are Cartan forms.
So lambda bar, D bar, it's horizontal de Rham differential graded algebras. That's all.
Horizontal. Okay.
Lambda bar, D bar, it's horizontal algebra for me. Or if you want de Rham horizontal homology of this algebra. H bar.
And how total derivatives acts on D bar?
On lambda bar.
No, total derivatives on
D bar, small. It is a composition of it is a combination of total derivatives. Okay.
Yes. So they act on D bar. It's composition from the left. Yes.
From the right.
No, on the right, then it would be zero.
I asked Volodya.
No.
On the right, it's in denominator. So multiplication from the right would be zero. So probably from the left.
I would say from the right.
At least when you expose the definition, it was action from the right.
It is from the right. Yes.
No, but in definition, the composition from the right is written in denominator.
In the denominator, yes.
In denominator, where?
In the definition.
In the definition.
Yes.
Here.
Yes. It's yes. It's from the right.
So from the right, it is zero action.
We quotient by this right action.
Yes, so we need some non-trivial action to have the RAM complex.
Yes. So once again, we need first of all we need the exterior algebra. Yes. So we have exterior algebra of diffiety, and we quotient by this ideal, Cartan ideal. Okay, and we take the d bar operator, which is a combination of just combination of d bar x and total derivatives. So differential d bar, it is a combination of total derivatives and d bar of x in coordinates, on coordinates function, yes or not? And this we have a horizontal complex, differential graded. I don't understand what is wrong here.
No, nothing is wrong. I just want to be sure that when you write this horizontal complex, you use multiplication by total derivatives by composition from the left.
You mean this one? Just a moment. You mean this one, that d bar equal to sum of di d bar xi. This?
Yes.
Yes.
How they act on d bar?
It is written how it looks. No. From the left.
No,
From
I
the
don't.
left.
Well,
It is from the left.
Володь,
I don't understand the question, Alec.
No, if they act by composition from the left, that's okay. I just want to be sure.
Yes, but it is written. No?
Where?
What here? Do you see
I,
or not?
yes, yes, okay.
so it acts on coefficients.
Yes. It's on coefficient, yes.
And if I, well, no,
Is it true or not that if we
you
take
cannot,
lambda bar, what is lambda bar? It is exterior algebra of diffiety
no,
factor
with
over,
lambda bar, it's clear.
yes, lambda 1, okay?
That's clear. Alec,
What's the differential? Differential is here.
yeah, we don't, with the left part of this small diagram, it's clear, but let's, so d bar, Alec, d bar are vertical operators, yes? If I understand correctly.
What?
D bar, D bar, D big, D capital.
D capital.
Yes.
It's a
They are,
differential operators, comma.
yes, they are all operated.
X,
Yes, so these are vertical differential operators with no DDX part.
yes. No, we call this. We kill this. Yes.
But on the previous page, it was written from the right
Where?
in
Yes.
different order.
Yes.
Okay, maybe I'm I was.
So
But
if
it should act on the coefficients, of course.
if the definition is correct as it was there, then it's not clear how this GG acts on
Let me check.
different
Let me check.
interferometers.
Let me check in the coordinates. We will see just right now. So we take G infinity. We have Cartan distribution.
Okay.
Okay. Then we have a vertical verticality condition. Okay, and we can write our vector fields in this splitting way. Okay, such that all this part has coefficients which are vanished. Okay.
So G bar consists of the second part in
Yes.
formula 8, yes?
Yes.
This part is exactly G bar.
Yes.
Okay.
Okay, so we have this connection, Cartan connection, of course, yes. And this Cartan connection, it is just a partial connection, yes. So this horizontal and vertical differentials, like as usual, we have
Yes. Okay, let's keep it.
RS form, yes, and this form can be written as a sum of such forms, okay?
I just want
we
to.
have a split, and we have split this for each p we have the direct sum of this on the level of infinite jets, and differential just in this exterior algebra usually like in Cartan case split it. I mean this Cartan formula.
Just a small but maybe important remark. All this will not work if you consider jets of submanifolds.
Yes, we consider jets of submanifolds.
No,
Yes.
then it's not correct.
What?
Well, all this splitting, Cartan connection does not exist, and so on and so forth.
Stop. This is a local picture. You
Yes,
have
but
you have Rn plus m
yes,
over R m.
yes.
Okay?
Locally, this is correct, but it is not
I
invariant.
no, it's not. I just want locally this splitting. That's all. Because I need these local formulas in local coordinates on my differentials. This is the horizontal differentials. It is x on f. You see, like I wrote before. And this is the vertical part. They are separately nilpotent, and they have this bicomplex condition. That's it is absolutely standard thing. So this is a part of vertical, and this is a part of horizontal.
Yeah, okay.
Okay, do I agree?
Okay, this is clear, yes.
Yes. Okay, now if we have this, we can consider this not only on G infinity, but we can also consider this this what I told you. It's like a local bundle R m plus n over Rn. And of course, if we write this complexes and write all these sequences, all vertical and horizontal complexes are exact. No homology here. This is just trivial, homologically trivial. But now we want to consider differential equation, which would impose condition that this complex restricting on this solution manifold or full equation manifold as a subbundle in this G infinity, it is no more exact, and that the why it is interesting to study this associativity in homotopy sense. So this you know better than me how to interpret different part of this complex cohomology in physical, say, or variational way. So, for example, if we take n minus 1, 0 cohomology, then we have conservation laws of our equation. And this what I didn't know, maybe.
Володь, какой Бломан?
Well, that's what I expected, that you will. I said that, of course, I was quoted.
It was stated by Vinogradov in 80s.
Yes, that's what I wanted to say.
But why do you refer to this?
Because Bloman gave it in more extended way, just because I told that Vinogradov also first. Also, some things were proven by Anderson and Nicky Cameron, but Bloman wrote beautiful paper, and I just wanted to mention. I knew that you will absolutely was sure that you will react, but I just to want to draw your attention and attention of people from seminar that probably Bloman paper you don't know, but it is interesting and gives some new hints. That's all. That's my aim only to mention him. That's all. Of course, it was known for Vinogradov, some dude, without any. Yes. Now let's come back to Merkulov condition in our case. In the case of so I remind you what last time we discussed in details, that how to write this complex in subcomplexes of coboundaries and cocycles for each graded component of our DGA. And then in the case of in our case, we remind that it is from general Merkulov setting. We can define mapping restricting on these LP subspaces like zeros, and on these boundary subspaces in this way. And now again a reminder of Merkulov theorem and what we can define in this theorem in the case of variational complex. First, lambda map in our case we have from this condition, like in Merkulov case. Second lambda, it's our multiplication, and then recursively like this. So from this q, which is inverse to q lambda equal to -1. And then you have lambda n consequently. And then we remind this theorem about quasi-isomorphism of H infinity structures on homology and initial algebra. And that's what we will explore in the case of variational and other complexes of PDEs. So first, from Merkulov theorem, it is immediately gives you that there is a infinity algebra on horizontal cohomology for various differential equation. We can just obtain these structures.
Well, I'm sorry, but up to this moment, what you said uh, is uh, is true for any bicomplex.
Yes.
No specifics of
No, 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 no. Now only we just want to check that.
up to item one in your possible implications. We didn't use the fact that
No,
we had
now we want to just to
equality.
now want to check what is interesting we can
Yes,
find in the case of
let
PDEs.
us proceed. Yes,
So
okay.
first, why A infinity structures related to this H zero cohomologies is a priori may be interesting. We will consider a few examples. That's what our aim, to consider examples of this structure this is probably non-trivial structure. See? So we need just to find examples with non-trivial H and n minus 1. And it is a very, very rich class of equations. So all integrable equations, and probably also you know this better, that examples of equations with this condition. It's KdV, Kamasa, and
But again, why do you need infinite number of non-trivial conservation laws? Hn minus 1, 0,
non-zero.
they are just, this is just the group of conservation laws, and it is not trivial if at least one non-trivial conservation law exists.
Because it is non-trivial. Because well, I need non-triviality because I want to.
No, of course you need non-triviality, but non-triviality, for non-triviality, you don't need existence of infinite number of
No,
conservation.
no, no, no. I need only one. It's enough. It's enough. No, no. I don't need. No, I don't need. It is just example of possible equations
Well,
which
as for the second example, uh, I am not sure that Nikki and In were the first who found this fact. Maybe it was
this
Sokolov. At
I
least
believe you.
he also has a paper. With this, it should be checked.
Joseph, this I wanted also to say that when I wrote some references, maybe you can correct me and you refer in other sources.
No, I'm not sure, but what I'm sure of is that Sokolov, with someone, I don't remember with whom, also wrote about the Darboux integrable case. Yes, and yes.
Anyway, I just want to show you a few just non-trivial examples from this list of this Merkulov data, which we computed and proved that they are really non-trivial. So first, for simplicity, we consider just scalar case with two independent variables. And then our computations will be easily to follow. So we need to compute, for example, the third term in our Merkulov data in the case of omega Q0 with horizontal differential. And then this lambda 3 on 3 tensor developed tensor VWY, we defined in terms of initial operator Q in this way. It's easy.
Володь, I don't understand this reference to Anderson and Cameron. Well, you need not to be Anderson or Cameron to see that in two-dimensional case there are only two lines in three lines in.
You mean in 2 dimensions, only in second order case?
It doesn't depend on the order.
You mean this one?
No, I mean this green example.
No. This is it's a moment. It is just a scalar partial differential equation.
Yes.
For simplicity, I have just.
Yes, this I understand. But what?
You mean okay? You mean that's the three column?
Yes, but it is three column by definition.
Okay, it is reference maybe how to say superficial. Okay, so we have 3 columns, and this simplify computations very much, because we can develop our algebra in 3 component, and then tensor product also can be developed in direct sum of this developed component I sub 1, I sub 2, I sub 3, and considering
Please recall what are these A's calligraphic.
we have a differential graded algebra. So
Yes.
we have component of degree 0, degree 1, and degree 2.
Okay.
Yes. And then if we have tensor product, tensor cube of A, then we can develop it also in each, to each E, we can write as a direct sum of corresponding graded component. Now we want to define how it may be used to compute this lambda 3, which defined by this. This lambda 3, because we can, we know that from this Merkulov blah, 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 from this, we know that restriction Q on, it's just a careful computation, on A0 equal to 0, then we have that lambda 3 on 0 component of this cube equal to 0. And also we can very easily check that restriction on the fourth and fifth and sixth, it is also 0, because we have in each case we have 3 forms or higher. And if we have restriction on 1, 2, and 3, then it is not a priori not necessary 0, and then we can take in v, w, and y from different component. For example, if we take v from a1, w, y from a0, then sorry. Then we have lambda 3 more simple, y q w times v. If we have v w, so we just have all possible things with non-trivial lambda 3. And in this case, we can explain this lambda 3, express it in more simple way. Only in the case when all they are have degree 1, then lambda 3 can be written in this as a sum of 3 wedge product. And then we using this, we can express multiplication m in our cohomology through this lambdas. So let's do it for special equation. That's of course the simplest example which we have discovered. It was the Burgers equation. In Berger's equation, we have H0 R and H1 generated by the following conservation law. So by the form U times dx plus U sub x U squared times dt. And then our, in this case, our computations for lambda, they developed in three cases. In so-called 3 cases, 6 cases, and 7 cases. So first, we need to define M3 restricted on the first component of H times the cube H tensor product degree 3. In this case, I don't know, I can make it more visible. We can take again, like before, V from H1, W, Y from H0. Then, by definition, M3 is a projection of my lambda, which is U times Q WV, and it is 0, because in our case, W and V product cannot be exact differential. We have this from our cohomology. And then we can check similarly, taking V, W, and Y, that M3 in each case can be equal to 0. This is the first case when we restrict it to H3. Then so-called 6 case. It is more developed, more complicated, but we also made all careful computations, taking restriction on degree 2 H3 cube and M3 through lambda here expressed like this. And it is also, one can easily argue that it is 0 for the same reasons, because V wedge W equal to 0. And all this, I don't want to spend your time. You can check all carefully that all these cases, all these 6 cases, they give you M3 equal to 0. The last, the most tedious computations in the so-called 7 case, when you restrict M3 on the degree 3 of your tensor cube. And then you also, fortunately, check that M3 equal to 0. It means that in all these possible non-trivial case, higher multiplications for Berger's equation, they are 0. And it means that this Merkulov lambda 3 is identically 0 also. So it is not abstracted associativity, it is really associative structure on the cohomology of this, on the horizontal cohomology of Berger's equation. Now, the next question, what's happened if we take not horizontal but vertical cohomology? For this case, one can, again, Vinogradov's two-line theorem, and take second-order equation of this form. And in this case, we have H0S R only for S equal to 0, and for other S, it is trivial. And it means that our operator lambda 3 for this case identically 0, and then all M3 in cohomologies equal to 0. So the only possible non-zero operator, it is just our multiplication. So we have, indeed, even in this case, we have a multiplication fully associative, not homotopy associative. Of course, we were a little bit depressed that all examples are non-homotopy associative, but
I'm sorry, why do you consider only H00? And why don't you consider the next line, H1 and H2?
we just consider algebra of type H0 dot.
Well, this fact
It is the fact that it is
concerning H0s, well, it is not true only for the equations of this form. It's more or less true for all.
well, Joseph, I was sure that you will find and you know much more than we about what.
No, I don't understand why you restrict only to the this cohomology,
Because because it is
H00, and
because it is just an evident example of strong homotopy, strong associativity, not homotopy but real associativity. And we wanted to find some vertical example. We have found the first. That's all. And then we wanted to find non-trivial example. It means we wanted to find something with M3 non-zero. Because otherwise it would be not interesting to compute these homotopy structures. And such example comes from this system, for example. That's what we succeed to find. Let's consider this system. And then we have the conservation law, which defined by some function f of u, such that first and second derivative non-trivial. And then we can take horizontal differential of this form, and we obtain that it is indeed conservation law. And that's V define the cohomology class H1. In the other hand, if we take function W, which is derivation of U, then dh of W gives you 0, and it means that W it's just a function. It's a H0 from H0. It's just a function. Now we want to use this W and V and to construct our lambda 3 like in Merkulov example. So in this case, lambda 3 is y times q of product W V. If we replace by representative, we have that lambda 3 gives you y times f of u. And then mu3, m3 of this v, w, and y gives by projection of this on H0. And we can choose f of u non-trivial, that the projection different from 0. For example, if we take y as a derivative of u and f1 plus u cube, then we obtained that this projection gives you a derivative of u, and then everything is non-trivial. So it means that probably in this case we can't find exact associativity even in this simple one column complex. So it might be associative in Merkulov sense only up to these conditions of Stashev type. So this is a non-trivial example. Then, of course, the product which we didn't explore because it is very difficult to compute. We just, of course, can can be impressed by so-called Massey product and cohomology, which in topology used very, very often. And then, of course, this Massey can define higher cohomological invariance for differential equations. Unfortunately, so our attempts to compute these structures, it was not very successful because the H infinity structures in this case are not they are in some sense not very well defined, and there is even discussion about this Massey product in math overflow. So we decided not to consider, at least in our paper and in my talk, we decided not to consider the computations of a higher Massey product. But it is possibly maybe a source of interesting higher structures for equations. This I don't know. And that's why I took this picture that this might be infinite number of invariants, cohomological invariants of differential equations. Okay, and then I will finish my talk with some formality results, because it was also one of our aims to check formality results. So we say that our equation is horizontally formal if the corresponding DJ algebra has cohomology, it's quite isomorphic to its horizontal cohomology algebra with trivial differential as a M1. So we consider it like A infinity algebra with, so it's a minimal A infinity algebra. And also we can define in a similar way dV formality, it means for vertical complex. And also we can check that this Merkulov theorem applied as well, and we have the same series of high multiplication like we considered in our examples and in theorem 4 of Merkulov in previous talk.
A question, and can you present an example of
Yes.
non-formal equation?
Just a moment. So what we have as example, formal equation, it's example of Berger's equation. That's what we checked. So it is our example with scalar. It is also DH formal. So that's what our computations showed. But this is important, that example 9, it's here.
You mean this overdetermined equation, yes?
This example with them, it's non-formal. This one.
And why how formality relates to overdeterminants?
Relates to?
Well, the only example of non-formal equation is this overdetermined equation. Maybe
Overdetermined.
yes.
That's a good question. This is a good question. This I don't know. Probably Probably it relates somehow, but this I don't know. It's a good question.
And KdV equation is formal or not?
I suppose that it's formal. I suppose it's formal. In the last example, it is also interesting example of formal equation. It's equation of Cauchy-Kovalevsky type. Then it is always DH formal. We can prove it. And this
Excuse me. So HS0, S is horizontal dimension or vertical? Horizontal, I believe.
horizontal.
And why Hn minus 1 is trivial?
Hn non-trivial.
No, Hn is non-trivial, and Hn minus 1 is this group of conservation laws, why it is trivial for Cauchy-Kovalevsky equations. Do you state that all equations of Cauchy-Kovalevsky type do not possess conservation laws?
I think we took it from Vinogradov.
No, no.
No?
The Gradov two-line theorem states that all lines except for the n and n minus first ones are
Yes.
trivial. But usually n minus first line is non-trivial because it contains conservation laws, cosymmetries.
Yeah, cosymmetry I understand, yes.
Yes, but why I don't understand item 1.
This one.
Maybe it's a property of Cauchy-Kovalevsky equations, but I doubt. I doubt that.
I don't remember, Joseph. We just I think that I don't remember. I should check it. Okay, let me
Because
let me check it. But
I think that it is wrong, but
you think it is wrong?
what do you call Cauchy-Kovalevsky type equations? Maybe by definition these are equations with trivial H1. Then it's true.
H1, yes, of course. Yes.
No, it's unclear. What is Cauchy-Kovalevsky type equation?
Which satisfies to Cauchy-Kovalevsky theorem. It's not. It is not necessary. Well.
But they may possess conservation laws. And Hn minus 1 is not trivial.
Yes, it might be wrong. It might be wrong. I need to check, but I need to check. I forgot why we suppose that it is H n minus 1. A priori, Cauchy-Kovalevsky might have.
Why not?
Why not? Yes. I'm slightly confused. Maybe I'm wrong with this. And And then these arguments might not be true. These arguments that all inductively all higher m equal to 0. If it is not, it might give also interesting example. Thank you. I will check it, Joseph. Thank you. Well. When I told you this, this might be discussed in infinitely, because number of such examples are should be infinite. If you supply me with some other examples, I would be very helped.
Examples of what?
Of non-formal, like
No, I thought that you will supply me with such example.
no one example of no this.
Yes, overdetermined, yes.
This might be
Well,
a good point. If it is true and we are wrong, it might be a good point that we can find.
did you try to compute something for equations of KGD type with
For KP.
for KP?
Yes.
Well, KP is a very complicated example.
No, but we have another how to say, we have another no, we didn't compute this Merkolov data for KP. It's too difficult, but we have another arguments why it might be formal.
Well, at least for some equation.
Because we have another model of differential graded algebra related to KP.
No, I mean some non-degenerate equation, or not overdetermined, with several conservation laws. Not maybe not infinite number of conservation laws, with 2, 3, 5, 6, 7.
Because it is without computer it is very difficult to compute, and
Oh
we
yes,
will.
of course. Well, for all these examples cannot
So
be
one,
computed.
in fact, one of my aims was maybe to how to say, to not to insist, but to propose maybe some young people to with computer to do these computations. And also Massey product is very possible source of Massey product for differential equations. It's very possible product of non-trivial invariants which abstract formality.
Okay.
It means that what we didn't succeed to compute, possible to compute with computer.
Well, well, if I supply you with an equation with say 5 conservation laws non-trivial.
We will try to do what the bet.
I'll send you.
Okay.
Yes.
And also, I will check this Kashi-Kovalevsky case, because
Okay,
it
okay. Yeah, I'll send you an example well, of some two-line but three-dimensional equation with several conservation laws, not with infinite number.
great. Then we can try to.
Perfect. I'll do it tomorrow.
Okay, thank you.
Well,
So
and
probably
for
should stop.
Volodya, I think that you, yes, Happy New
But
Year.
we did our best. You see,
So,
we did our best, because in fact, without computer, it's really very
yeah,
difficult.
well, of course. And for example, well, assume that all these uh, structures are computable. So assume that you know something about an equation in terms of these structures, of these homotopy structures. So what can we say about the equation itself, about its solutions, or for example, we know that equation is informal. So what? Or we know that it is formal. So what?
Well, formal equation should be simpler than non-formal. That's all what we say. They should be simpler in some sense, geometrically. But it is just a kind of toy model of higher structures for differential equations.
Well, what is it? For example, we know that
No, the point what you ask, we don't know the answer, but it is possible. What this formality says about overdeterminacy or
for example, yes, for example, or about its uh, useful homology, so about existence or non-existence of some structures like Hamiltonian, or I don't know.
Hamiltonian probably because if you know the interpretation of say conservation laws and maybe some kind of homological sense of noether
For
theory.
example, assume that we know that the equation is integrable in this, well, it admits Hamiltonian operator or infinite number of conservation laws. Does this property influence on your invariance?
Well, you see, let's consider Burger's equation, which
Yes.
we know that it is.
Well, a Burgess equation is well, it possesses infinite number of symmetries, and it doesn't
Yes.
possess conservation laws, well, except for the only one, which is equation itself. So what?
So it is you know all higher structures which we can associate with Burger's equation via this transfer Merkulov model. They are really associative, not homotopy associative. It
For
means
example, Volodь, for example, well, well, there is a paper, maybe several papers by Artur Sergeyev and Roman, forgot his. Uh, mm,
Roman Popovich.
yes, Roman Popovich.
I think that
It is
sure.
proved that even order equation may possess only finite number of conservation laws. This is more or less obvious. So, is it possible to compare Burgess with some other simple second order equation which possesses, say, four conservation laws? As I remember, it can be only even number of, because maybe I'm wrong, I'm not sure, with 3 or 4 conservation laws.
Even with three conservation laws, it would be interesting.
Okay, I'll send you a less trivial example
Then we
with
can
several
compare it
conservation
with.
laws. The number of conservation laws is bigger than 1, but less than infinity. So I'll send you tomorrow. I'll write it down.
Let it be better 3.
3.
Yes.
I'll see, maybe 3. Okay, but I'm not sure. Okay, but I'll.
So it would be very disappointed if the answer will be the same, and it will be very.
No, but no, it's not a matter of disappointment. It's just it's completely new approach, and it is interesting
Look.
to collect some experimental data. Okay, I have too many questions.
Yes.
I think it's time to finish. Volodya, спасибо. Oh, thanks a lot. Questions, remarks?
I'm sorry that I just forgot something, and probably this Kashi-Kovalevsky, it's a real
Well,
mistake.
check the mistakes. Yes.
I will check.
Uh,
Okay.
Yes, I'd like to ask one very simple question. Is it true that these algebraic structures are invariant?
Invariant with respect to
change of coordinates of our equation?
you mean with respect to diffeomorphisms?
Yes.
With respect to symmetries.
No, if we rewrite equation in different coordinates, will the result be the same?
Well, but if you write the only question if the homological structure of Vinogradov sequence invariant with respect to the diffeomorphisms or not?
Yes,
Of course,
invariant.
of course.
Vinogradov structure is completely.
So if the algebra structures of this spectral sequence is invariant, then what we say it doesn't depend on
Sure.
No, the
For
algebra
example,
structure, I don't think on the level of forms or homology.
on the level of cohomology.
Uh,
On the level of cohomology.
well,
Or
probably Volodya is right. I'm not sure, of course.
it looks like
Volodya, for example, take the same Burgess,
okay.
but denote using new notation, denote u x by v and write it as a
x by z
u x by v.
by v. Okay.
Ux by v. And you will yes, and rewrite Burgess in terms of u and v now. It will be a system.
Yes.
And it will be evolutionary system in terms of v.
Okay.
And no, not this example. I mean Burgess.
No, I understand, but to compare.
And rewrite Burgess as an evolutionary systems in terms of v after this relabeling. Yeah, will the result be the same or not? Of course, conservationist laws, in this case, just one law will be the same because conservation laws are invariants.
Of course. So they just rewrite this form alpha will be rewritten in terms of v.
Well, to be more formal, you have edified, as you say, a pair E and C. Yes.
Yes.
Okay. Does your constructions relate only on this pair or on the way how you present it in coordinates?
V, W, and Y. We need just only this.
No, I think it must be thought over. If you didn't check it, then you will not answer immediately.
Immediately not, but I'm pretty sure that
You understand that this is the most important thing.
of course. but I think it is.
Well, it seems that it really depends only on horizontal cohomology, which is completely invariant.
Yes.
But nevertheless, it should be checked.
Mm-hmm. Okay, it's also good point to think. Yes. Well, I need to compute immediately. I can.
It's the crucial point. Okay, thanks. More questions?
Mm-hmm.
Then, Volodya, thanks a lot again. And now we meet, I think, in February. Okay?
Why in February?
I thank you for being with us and see you more or less in a month.
Why in February?
Because we have holidays.
Holidays?
Yes.
Stop. Today is 8, then 15.
Yes. You know that all seminars and lectures in Russia stop in February, in January, even in December.
I forgot completely. I forgot.
Yeah.
Thanks for to remind me.
Okay. Thanks a lot.
Okay, let be in touch because I want to
Yes, yeah. I'll contact you tomorrow.
thank you.
Okay. Bye-bye.